All right, so maybe this notation here is not something that we've used exactly the same way. What this means is that these are the coefficients of the vectors in the basis B. Well, B has two vectors, B1 and B2. So here we're writing, and in fact, you see that B1 and B2 both have three components. But here you only have two components. Why is that? Because this means that I'm that.
B1 and -2 of B2?
Yeah, that's exactly what it means. So what this actually means, I don't know what that was. What this means is just 2 minus 2b. The meaning of this is 2 times b1 plus -2 times b2. That's what it means. So just to to make sure we're on the same page, can you tell me what that is?
2, 4, 6 plus -6, 4, 1. And you just add the components.
Yes.
So that would be negative 4, 0, and
Oh, this is plus 4, right?
oh, is it okay?
I think, isn't it? Because -2 times -2.
Absolutely.
Yeah.
So -4, 8, and 8.
Okay. All right. So that's what this notation means. All right. So. All right. Now here's a good one here. Express this vector here, 2 minus 4 minus 4, as a two-component vector in the basis B. So
Okay.
what you want to do is set up an equation here for x and y.
Right.
So if you tell me what equation to set up.
Well, you want to do it in vectors, or you just want to name the vectors, like B1.
No, I would do it using the specific vectors.
Okay, so it's some linear combination of B1 and B2, so it'd be X B1, or 1, 2, 3 times Y 3, -2, -1, or plus
Okay.
Y. I mean,
Okay.
am I on the right track there?
Yes, you are. So what's this equal to?
2, -4, -4.
Yeah. Okay. So you're more than 50% done. So what do we do here? How do we solve this?
Set it up. Oh, let's see. Well, we got three equations there, right? So
Yes.
x plus 3y equals 2.
Yeah, we could do that. But I think one of the things we've been learning is that instead of going from matrices to equations, you want to go from equations to matrices.
Right, so we set it up as a matrix.
Right. So how would we do that?
Is it going to be an augmented matrix?
We can do that, yeah.
So the first row would be 1, 3, bar 2. Next row would be 2, -2, bar -1, 3, -1, -4.
Okay. All right, now, in general, this may not have a solution. But I'm thinking they worked it so it does. Well, let's continue to work it through. What do we do now?
Now, I'm thinking that I can't recall at this moment. What do we do now? Do we factorize it?
Well, I row reduction.
Okay, do it to the reduced row echelon form,
Yes.
and then be the answers. same to both sides.
Yes.
Okay, so,
So what operation should I do?
well, these two elementary row operations would be row 2 minus 2 of row 1.
Okay. I think I can do two row operations at once here.
Yeah. So row 3 minus 3 of row 1.
Okay. Yeah, I think we can safely do two of them. You can as long as the base row is different. So here we still have 1, 3, 2. This one here becomes
0.
0.
And then 2, okay, so 6. So it's a negative 2 minus 6, which would be negative 8.
Right. Then this one.
And 4. So negative 4 minus 4, which would be negative 8.
Okay. And then how about this one? I've got this.
0. All this addition to put me on the spot. Okay.
Yeah, no, yeah. Well, if you can do it on the spot, that means you can do it.
So negative 9, so it'd be negative 1 minus negative, minus 9.
Okay.
So it'd be negative 10. And then negative 6 minus 4. No, sorry, negative 4 minus negative 6. So it'd be also negative 10.
Yes. That's good news, isn't it?
Yeah.
What can you do with those last two rows?
You can divide by, well, would you even do that? Or
I wouldn't.
they're dependent, so
Yes, they're dependent. So I can replace that last row with what?
zeros.
With zeros. I would just jump to here.
Yeah.
And then what about the second one?
Well, try to get that leading negative 8 to be a 1, right?
Yeah.
Oops. Okay. So we could add 8/3 of the first row to it.
No, you don't. No, you don't do that. There's something there. You have to use a different row operation.
Okay. Would we just divide by 8?
Yes.
Negative 8?
Yes. And I would just leave this. Now at this point, you don't really need to reduce it any farther. You can read the solution off of this.
Right. So that would be,
This is actually LU decomposition. This is in U form.
yeah. So, do we need to get the lower?
Yes.
So we can solve it?
Yes.
I just did a problem like this. I just did, and now, see, this is great, Dr. Thorne. Now I know what my students feel like, even though they feel prepared before they walk into class.
Yeah. No, that's what makes this really valuable, I think.
Yeah. Well, it's teaching me, to be super patient with my students. So let's see. We got to get the lower.
Yes.
And to get the lower, we need to figure out what we did. We need to take the inverse of what we did to.
No, you don't. You don't have to. It's a lot easier than that.
Easier than that. That's great. That's
Yes.
good news.
You can read the equations, the new equations, directly off the matrix. Remember,
Okay.
this is the x column, this is the y column. I could call this the ones column.
Okay. So you're saying that y equals y.
Well, no, this is the ones column, not the y, not the y's
equals
column.
1.
Yes.
And if we substitute that there,
Yes.
then 1x plus 3 equals 2. So
Yes.
that would have to be negative 1.
That's
so x
it.
equals negative 1.
So that's the answer. Now, of course, you can always go back and check. So if you put minus 1 here and 1 here, so I take the negatives of these and add them to this. Minus 1 plus 3, minus 2, minus 2, minus 3, minus 1, looks like it works.
See, now is that always possible, or maybe to
Yes.
go direct?
You should always check. Don't you teach your students that?
Oh yeah, check the answer. But I'm saying, is it always possible to go if you get your upper and you've got this augmented upper triangular thing? Can you always?
Yes, you
You
can.
don't
Yes,
have to find it yourself.
that's called back substitution.
Okay.
You can always do that. So you don't have to reduce all the way as long as, and you can see the procedure. You get the last variable, and once you know the value of the last variable, then you plug that into the equation above it, and then you just keep unzipping. If you had more equations, you would just keep unzipping all the way up.
Okay.
So that's a very good technique.
All right. I was just looking at this last problem I did before the class.
Uh-huh.
It was one of these, and it was a little bit more complicated, but just I'll go back and check that later.
Okay.
See if I can do it that way.
All right, let's look at this problem, this next problem. I think this one's fairly simple, but it's also a conceptual thing. All right, here, so this is the next problem. Number 2, let U1 equal 0, 0, 1, 0. Now, this is a matrix, but as we've been emphasizing, matrices are also vectors.
Right.
So here's one vector, here's another vector, here's another vector. Three vectors. So, and U is the set of these 3 vectors. And U prime is also a set of 3 vectors, but I'm negating the second vector.
Okay.
All right, so now, express 5, 4, 3 minus 5 in terms of the basis U and in terms of the basis U prime. All right, so take a minute and understand what that's saying. Once you understand what that's saying, it's not difficult. The hard thing is what is this actually saying?
So the bases are the 3 vectors.
Yes. So start with U. Yes, those are 2 different answers, right?
Right.
So
So 5, 4, 3, negative 5 is
Yes.
a linear combination of U.
yes,
Also a linear combination of U prime, depending on what basis you use.
yes,
Okay, so when we're trying to express 5, 4, 3, negative 5 in the basis of U,
yes,
we need to figure out how many of U1 and how many of U2 and how many of U3
yes.
we have to put together to get to that. And it looks like it would be 5, maybe.
Can you read
I'm
it?
guessing 5, 4, and 5.
5, 4, and 5. Okay, so you're saying 5 U1?
Yeah, but I was just only basing that off. No, 3.
All right,
Three, because-
yeah, I think 3 is better.
Yeah.
3 is better. I like
Yeah.
that answer better.
And then 5 of 3, U3,
Yes,
and 4 of U2.
right. So you would write this as 3, 4, 5 U.
Okay, and then in U prime,
Yes,
since U2 is negative, and that was where we got the 4 from, that would be negative. So 3 U1 minus 4 U2 plus 5 U3.
well, it's actually, you should say minus 4 times minus U2. Right. because the second basis here is, actually the best way to do it would be this. Whoops. Okay, here we go. I would say 3u1 prime minus 4u2 prime
Yeah.
plus 5u2 prime, u3 prime. So that's going to be 3 minus 4, 5 u prime.
Right.
Okay. Now, I think you can go backwards. This is going backwards, right? Can you
Yeah.
see how to do part B here?
Sure. It would just be a matter of figuring out, multiplying those basis vectors
Yeah.
by those amounts.
All right, so let's skip that and go and let's look at another problem. So this is kind of warm up. Let's see. These are solutions. Let's look at this. Oh, okay, this is good. Let me copy this page here. Got move or copy, and then we'll just move it to the end here. All right. So let's go ahead and do. Let me look at this top one here. Well, no, that's too. I think that's. Actually, I think there's some emphasis in the book that matrix multiplication is the same as composition. So that should be easy. Now, all right. So let's look at 3. All right. First thing is to, of course, is to read the problem. Find the matrix for ddx acting on the vector space via polynomials of degree 2 or less. In the ordered basis, this is important, ordered basis b equals x2, x squared, x and 1. Note that in this case, b is being used as the basis for both the domain and the range of the linear function.
Right.
All right, so is that making sense?
Just a polynomial, kind of standard form polynomial. And then the matrix for the, I guess, the derivative of that would be 2, 1, 0.
Well, almost. But here, let me just snip this and paste it. I want to do this one at a time. Okay, so let's see if I copy it and paste it down here. It should be fine. All right, so, all right, now, this is a function. What you have here is ddx is a function from v to v. Okay, let me put my lines on too. Okay. All right, so now what this, now an element of v can be expressed as let's see, I can express it as ax squared plus bx plus c. Right? So you want to know what ddx does to an element like this. So what should I write?
Let's see. And the matrix, so I guess the matrices would be the coefficients A, B, and C.
Well, let's not get to the matrices. Let's just do the calculus first.
Oh, okay. 2ax plus b plus 0.
Okay. Equals 2ax plus b plus 0. All right, so now let's try to interpret this in terms of linear algebra. We want to know what what we want to know is that what does ddx do to the vector ABC? All right, now ABC is expressed in the basis B.
A is the coefficient of the squared term, and
Yes.
B is the coefficient of the, and C is the constant.
So do you see that this here is this?
Right.
So I want to write this one also as a vector. How can I write this as a vector in terms of the basis here?
So it'd be 0 x squared terms
Yes.
and 2 linear terms, and then looks like 0 constants.
All right, so this is in the back. So what you say is that this here,
One constant.
one constant, okay. All right, well, but let's see. Is what I wrote down correct?
Well, let's see, 0, 2, 1.
Yes.
0, 2, 1.
And here I have 2ax plus b.
Like in that basis, I guess, you don't have it. It looks correct, I guess.
All right, now the basis is, remember that b is equal to x squared, x, and 1. All right, so this here is, you'd call this b1, this is b2, and this is b3. So in other words, this vector here, right, is 2 times b2 plus 1 times b3.
Right.
So there's something missing.
The 0?
Well, here you have 2ax plus b. Here you just have 2x plus 1.
Oh, the A is missing.
The a is missing. And
The B.
the b. Does that make sense?
Okay, but could you separate the A and the B into a separate vector? I don't know why you would, but
Well, yeah, we'll get there.
Okay.
So what we're saying is that ddx maps the vector ABC to the vector 0 to A, B, like this. So now all we have to do is find the matrix that this, we have to find the matrix for this. Let's see, there are a number of ways to do this. But I could write this, what I could do is I could write this as A times, let's see. Well, I don't know what's the best way to do it.
What was the question again?
I want to find the so here, I'll write the question.
No, I mean, you had it written down.
Oh, okay, well, okay, so let's. Find a matrix for ddx.
On the vector. Okay.
So the strategy here, if you want to get the strategy is express your vectors as linear combinations of the basis, and then find the matrix that relates the coefficients of the input to the coefficients of the output. right? This was an arbitrary element of the domain. This is an arbitrary element. This is what it yields. This is what comes out. So we know because it's a linear function, there's going to be a matrix that gives this function. And what that means is there should be a matrix fill in the matrix.
Top left is going to be 0.
Yes.
And it's a 3 by 1. I mean, can it be a?
Well, no, it's not a 3 by 1 because your output. All right. So how did you compute this? This is a 3 by 1. This is a 3 by 1.
Yeah.
This one has to have the same number of columns as this has number of rows.
Right.
So that has to be a 3, and then the output has to have the same number of rows as the output here. So
Yeah.
this has to be a 3 by 3.
Yep. Okay.
Now take this one at a time. This top entry here comes from the top row here times this
All
vector.
zeros.
So they're all zeros. What about the second row?
It's only going to have the first. It's only going to have one of the first. It's going to have the first element of the
Okay.
column. The 1 or 2. It's going to have 2.
It's
of
2,
them.
yes.
2, 0, 0.
Yes. And then this
And
one.
then 0, 1, 0.
Yes. That's it. That's it.
Oh,
All right?
so cobwebby.
Well, so, I mean, what you got to, this is an important process. Once you get the process, then it becomes easy. But that's what I like to do. Express your arbitrary vector in a domain as a linear combination with unknown coefficients. And express the output the same way. Then find the matrix that relates the two.
Nice.
So I think that's a good way to look at it. Let's see if we can have, I don't even know how much more time I have left. What time is it? It's not showing me anything.
6:04.
All right, well, we've got another 6 minutes, so okay, let's see.
Use that matrix.
Let's try C.
Good.
Find the matrix for ddx acting on this vector space. X squared plus x squared. Here, I'm going to write it here and then copy it down. So it's the same operation, but you have x squared plus x, x squared minus x, and 1. So let me just copy that down, because if I don't copy it, I won't remember it. I guess this was part C or something. All right, so this is my basis. Oh, but what's the range? Is that the basis for both of them? Yes. Okay. Yes. So that's the basis. That's the basis for both of them. So because the time is short, let me just write down the equation that you want. You want to find ddx of a times x squared plus b times x squared minus x plus c times 1 equals question mark. So here's the place where you use calculus. So what do I write over here?
C. A 2x plus 1
Okay.
plus b times 2x minus 1.
Yes. And that's
Plus
it.
this.
That's it. Now this vector here can be written as A, B, C in my basis. I think they call it B prime or something.
Mm-hmm.
Now the wrinkle here is that we want to write this vector using this basis. So I'll just write this like this: 2x plus 1 plus b times 2x minus 1. So I need to express this using the basis.
So would you have to distribute the a and the b and then combine like terms? And then
Yeah, we can do that. So this is going to be 2a plus 2b times x plus a minus b. Okay. Sorry, you got a political call. Okay, but I need to express this in terms of this basis.
So x.
Okay.
Maybe that didn't help.
All right. Well, let's see how we're going to do this. Trying to think of a good way to do this. Well, let me just do this. This is a non-systematic way. But we're getting towards the end. But here, notice that if I take x squared minus x squared plus x minus x squared minus x is equal to what?
Uh, 2x.
It's equal to 2x. So in fact, why don't I divide by 2? And I get x here. Now, I can substitute this x in for this one.
Mm-hmm.
Now, why did I do that? Because, as I said, I want to express this polynomial in terms of these three. Now, there's a more systematic way of doing it, but that's basically what you have to do. We can do more of these. We can do more of these on Friday, because I think this kind of reasoning is very good. So, in fact, what I have here is 2a plus 2b times x squared plus x minus x squared minus x over 2 plus a minus b times 1. And I can further write that as a plus b times x squared plus x plus negative a plus b times x squared minus x, then plus a minus b. Now notice I have my three basis vectors. Basis vector 1, basis vector 2, basis vector 3.
Mm-hmm.
So this is equal to a plus b, negative a plus b, and a minus b in my basis. I think I did too many steps, but the point now is that when we started out with this vector here, ABC, we computed the derivative, We re-express the derivative in terms of the same basis. So in fact, I can say d dx takes ABC to this all right, and then now we need to find the matrix for this. So can you find the matrix for this? First of all, what size is it?
1 by 3.
All right, so this is my input. It's a 3 by
1.
It's a 3 by 1 input, and I get a 3 by 1 output.
Right. So let's see, it needs to be a 1 by, or 3 by 1.
All right. So,
Or 1 by 3. It has to be a 1 by 3.
okay, so we have 1 by 3. So how do I write the matrix equation here?
Matrix equation.
Where do I put my ABC?
Isn't it just on the left?
Yes.
Are you talking about in the vertical? So it'd be a vertical vector, or a column vector, ABC.
Okay. Right. And then what do I write on the right-hand side here?
Looks like B, negative B. No. How does that work? A plus B.
Well, remember what we did up here. If it will take me there. Well, eventually it will take me there. Remember what I did over here. Right? I said d dx takes this vector here
Mm-hmm.
to this vector here. And I said find the matrix that gives this function.
So many rows of that.
So I wrote this vector on the left, this vector on the right, and then I wrote down a matrix.
Mm-hmm.
So help me do it down here.
Sorry about the noise.
No problem. So help me do it down here. It's an analogous problem, analogous setup here.
A, B is one of those. So 1.
All right, well, I need to write a vector on the right-hand side here. What do I write on the right-hand side?
Oh, I thought it was A plus B,
Yes.
then negative A plus B, and A minus B.
Yes. All right, so is this really a 1 by 3? It's 3 by 1, this 3 by 1. What does this have to be?
Uh, 3 by 3?
Yes. 3 inputs, 3 outputs. 3 by 3. 3 by 3. So let's go one row at a time.
Okay. So we need an A plus a B. So
Yes.
I'm going to go by row.
Yes, go by row.
So 1, 1, 0.
Yes.
And then negative 1, 0.
Yes.
And then 1, negative 1, 0.
Okay, yes. Now you can actually go by column too. Just notice here that what you have here, I think we mentioned this before, but if you write this left-hand side here, if I write this like this, I can write it as 1 minus 1, 1 times A plus 1 minus 1 minus 1 times B plus 0, 0, 0 times C, right? If I break this up into the A part, the B part, and the C part. So notice what we have here. These are just the columns, right?
Right.
This is this column, and then this one here is going to be this column, and this one's this column. So you can get it by columns. All right. Well, I think our time is probably pretty much up. I think it's very good that we work on this, because it's important to get this concept. So it's good to think about this. What we're doing here. The key here now is that we're expressing vectors in terms of bases, and the basis may consist of vectors that are unusual. Like this basis here, these vectors are kind of unusual.
Yeah, I'm definitely going to go back and relook at this example.
Yeah.
And I was going to ask you how to get to the other problems. I guess I never didn't have that link to the page with the tabs.
The page here. Okay, so let me. If you go to the YouTube, page.
Yeah.
To the actually, I don't know if I have the unlisted page. No. If you go to the UC Davis page, you go to on the first page. There's a link to the OneNote notes.
Okay.
And it should be there. Let me just check.
You asked the question earlier in the session, and I just said, yeah, sure. But I thought I did, but when I looked for those tabs, I couldn't find it. So.
Okay, so let's see. UC Davis, linear algebra. YouTube, I should come up for me. Whoops. Oh, okay, here we go. Let me pull it over so you can see it. All right, it should be on the, whoops, it's down, well, on my notes, this one here.
Okay.
So you
Gotcha.
you grab that, let's just check and make sure it works. And you should be able to view it here. And something's happening. All right, here we go. Matrix multiplication. It'll take a minute. All right, so chapter 7. Not the fastest response. But once it goes to chapter 7, then the tab should show here. There we go. So it should show here. I'm not sure that the notebook has updated so far. No, actually, I think it has. This is what we've just been working on right now. And the stuff that I've done they should be down at the bottom.
Yeah, there's number 3.
Yeah. It may not have updated, but it will. I'll make sure that it updates.
Okay. Well, again, thank you for your time.
Okay, sure. We'll do more of this next time. I think let's just stay in chapter 7 for a little while, and then we'll go to chapter 8 next week. Because I think this is important because it gives the intuition about how the idea of basis is really key in linear algebra.
I just think I need more practice with it because, last week I was doing it, thought I had it, but then it dropped it on me this week, and obviously I didn't have it.
All right, well, I'll tell you, if you go to this OneNote page, there's some better exercises. All right, they're better exercises than the web work, so you can look at those. And we'll do some on Friday, too.
All right, will do.
Okay. All right, good. So I'm going to stop this recording.